So I'm going to discuss transpositions in various abstract algebra books. I've got a good number here, 7 of them. I'll start with Gallian. But in this video, even though it's going to be like previous videos that I've made that are concept in books, go through books, show what they are, show the theorems. In this case, I'm actually going to work them out. So I'm going to show what they look like in Gallian, then do a few of them, then show sequentially each of the books, and just pick examples until I've done a whole bunch of them. Now, there's nothing, in the beginning when I first came across transpositions, I thought, oh, I cannot understand them. Wow, that's troubling. But in reality, what I've learned is, now that I've used them a lot, transpositions, which is really just cycles of two members, 1 to 2 or 1 to 4 or 4 to 5, are used to figure out whether something is an even or odd permutation, especially when you're working with the alternating group. All right, that's really what I have seen them used for. And so there's a way to take any permutation and break it out into 2 cycles. And what that really is useful for is for even and odd permutations. And so now that I understand that, these mysterious ways in which a permutation can be broken up into 2 cycles, and there can be arbitrarily many. Of course, they're always going to be either even or odd, based on whether that permutation is even or odd. There's nothing mysterious about them, and there is no theorem that tells you all the different ways you can do it, even though there is a way to break them out. And I'll show when I write them out. The way you have like 1, 2, 3, 4, 5. You start from the back and you go 1, 2, 3, 4, 5. And I'm gonna zoom in for this. Sorry about that. Let me zoom in a little further. 1, 2, 3, 4, 5. It's really 1, 5, 1, 4, 1, 3, 1, 2. And you can also write it as 5, 1, 5, 2, 5, 3, 5, 4, as shown here. But these other mysterious combinations are really just somebody knows that they're equal to that, and that's where, I mean, in this case is a good example. Somebody just knows that that's the solution. There's no theorem about it. Okay, so I'll stop there for showing the book, for showing Gallian. And then in the next little bit, I'm going to calculate a few of them so you can see how easy it is. I'm going to work through a couple of examples from Gallian. And so the permutation 1, 2, 3, 4, 5 can be written in a permutation symbol as follows. Where you start with here, and where you end up in the second row. So 1 goes to 2. 2 goes to 3, 3 goes to 4, 4 goes to 5, 5 goes to 1. Okay, now this also equals these 2 cycles. Okay, 1, 5, 1, 4, 1, 3, 1, 2. Okay, but you can also write it from the back. Okay, going this way: 5, 4, 5, 3, 5, 2, 5, 1. So it equals 5, 4, 5, 3, 5, 2, 5, 1. Now I'm going to do it, the way that I do it is I lay them all out. So, for example, this one, and of course you always apply them from right to left. Okay, so really you're going to do 1, 2, then 1, 3, then 1, 4, then 1, 5. Okay. So 1, 2, you flip these, then 1, 3, flip those, 1, 4, flip those, and then finally 1, 5. And sure enough, you end up in the same place. Okay? Then when you do this one, you're going to do 5, 1 first. So you're going to do 5, 1, then 5, 2. See how you're migrating that 5, right? 5, 1, then 5, 2, then 5, 3, and then 5, 4. Okay, 5, 3, I'm sorry. And there you are. You're back where you started again with having the same result. Now, of course, Gallian also has one that's a bunch of them. So it's 1, 3. Let me see if I don't go off camera. 1, 3. There we go. I'm going to do it right here. 1, 3, 2, 3, 2, 5, 2, 1, 5, 2, and 5, 4. Okay, so you'll see that this also yields the same result. But again, somebody just worked this out. I mean, there's no like theorem that says this is how it should be that I know of. Okay, so we flip the 3 and the 1, then the 2 and the 3, then the 2 and the 5, then the 2 and the 1, then the 5 and the 2, and then finally the 4 and the 5. And sure enough, we end up at 2, 3, 4, 5, 1, which is the same as 1, 2, 3, 4, 5. Now the origin story where it all began for transpositions for me was in Pinter. I was reading it during my commute, and I came across this line right here. And I remember staring at this for, I don't know, it seemed like hours. I just couldn't make out why there were all these flips. And just as the example that I worked out before for Gallian, yes, 1, 5, 1, 4, 1, 3, 1, 2 is the canonical way, and also 5, 4, 5, 3, 5, 2, 5, 1. But then, just as Gallian did, Pinter's got a 5, 4, 5, 2, 5, 1, 1, 4, 3, 2, 4, 1. So he does a few flips in here. So the 5, 4 is the same, but then he goes off and does something else. So that's just the way it played out in Pinter. And I'm going to work out this example too, but I'm also going to talk about a few other books so that I have a good set of examples to work with. Okay, so in the case of Rotman, I mean, you'll see the same theme book by book by book, where they'll show the 1, 3, 1, 2 and the 3, 2, 3, 3, 2, 3, 1, which is also 1, 3. You can always flip these. But then Rotman's got a few others, and I'll calculate these just for fun, just because they're all a little fun. And then in the case of Reis and Rankin, he's got a really interesting, they have a really interesting example that I think just for fun is worth working through, because they have a whole bunch of them. And then it gets routed down to all these 2 cycles. So yeah, I think these are normally written. So 1, 4, 1, 3, 9, 1, 9, 3, 9, 6, 9, 2. Yeah. And then 4, 5, 4, 3, 4, 7. 4, 5, 4, 3, 4, 7. And then 7, 9, 7, 8. So yeah, this is a normal way of writing out what this permutation is doing. But just for fun, I'm actually going to calculate this one as well. Why not? And then in the case of Silverman, Silverman also has another one of 1, 2, 3, 4, 5. So it seems to be a common theme that in every book after they talk about transpositions, they'll do a normal write out. 5, actually this one is a little different. Yeah, 5, 1, 4, 1, 3, 1, 2, 1. I should calculate this one as well, just for fun. Yeah, just to show that it is correct, that it works out. Yeah, more examples. I'll work these out just because I want to have some fun. And then in the case of Hungerford, Hungerford's got, he's got the basic one, the 1, 1, 2, 1, 3, Yeah, he just does the basic one. So he doesn't go he doesn't have the those examples that go all over the place, basically. And then finally, Rotman graduate level, the graduate level Rotman book just has a 1, 2, 3. And I'm not going to work that out because by that time, I think we would have had enough fun doing all of these transpositions. I'll work out the example from Pinter. And it goes 1, 2, 3, 4, 5 is equal to 5, 4, 5, 2, 5, 1, 1, 4, 3, 2, 4, 1. Now this is similar to this one. But you'll see that so it's got that and that, but then that 5, 3 it's just a little different. So let's calculate it out. Nothing profound here, folks, just having fun with transpositions. Okay, so of course you go from right to left. So it's 4, 1, 3, 2, 1, 4, 5, 1, 5, 2, 5, 4. Oh, I always want to write the same number again. I don't know why, but it's 3, 2. Then 1 goes to 4, and I did it again. Then 5 goes to 1. 2 goes to 5. And you see now how we're getting to our desired result, right? And of course, one goes to 2, 2 goes to 3, 3 goes to 4, 4 goes to 5. So this is, yeah. So that happens to be Pinter's example. Then in the case of Rotman's undergraduate book, I think we have space here, and I have books dropping all over the place. Rotman's example is 1, 2, 3 is equal to, of course, we know from before that we can just go like this, or we can go like that. So this is really 1, 3, 1, 2, or 3, 2, 3, 1. And of course, as you saw how I did these, you can always flip these. 4, 1 is the same as 1, 4, right? And 5, 1 is the same as 1, 5. I mean, we're just switching them, so it's always they're all going to be the same symbol. Okay, but the example from Rotman is 1, 3, 4, 2, 1, 2, 1, 4, 2, 3, 2, 3. Now, of course, here's a trick. Okay, any symbol, okay, when you do these 2 flips in a row, and of course you're always going from right to left, right? When you do these flips in a row, you're doing nothing, right? Because if I have 2, 3, 4, 5, 1, and I flip 1 with 3, and then I flip 1 with 3 again, I end up where I started, right? So really, before we even do any calculations, we know that all we really need to do here is this, okay? And then 1, 2, 3, so let's do them. 1, 2, 3. We're going to do 1, 4, from right to left. 1, 2, 4, 2, 1, 3. Oh, I'm sorry. There's a 4 there. Okay, so 4, 1. Then Oh, yeah. Very common mistake that I make. I just write the same number again. 2, 4, and then 3, 1. Okay, so this is 1, 2, 3, 4, right? 2, 3, 1, 4, which equals 1 goes to 2, 2 goes to 3, 3 goes back to 1. And of course, the 4 is ignored in these symbols. Okay, so we worked out a couple of examples. I'll do a few more in another clip that will be added to this video. Now for this example, this final example, we are just gonna have fun, okay? By now, everything that we wanted to do with transpositions, just to demystify them, I hope has already been done. So the example in Reis and Rankin, which of course you can do with any one of the many examples that are given in various abstract algebra books. So first I'm going to calculate this out, but of course this is written as, and we're going to do 1, 4, 1, 3, then we're just going to do it this way, right? So really that's going to write out to 1, 4, 1, 3, 9, 1, 9, 3, 9, 6, 9, 2, 4, 5, 4, 3, 4, 7, 7, 9, 7, 8. Okay, so I'll do the I would say the one on the left, and of course you always go from right to left. So this is really S9, right? This is an example in S9. So it's going to be 7, 8, 9, 4, 7, 3, 5, 9, 2, 6, 3, 1, 1, 3, 4. That should give me the final result. So I just want to know what the answer is for the one that's this right here, the one that's not 2 cycles. And then we'll do all the 2 cycles. Okay, so 7, 8, 9, 7 goes to 8, 8 goes to 9, and 9 goes back to 7. And these are not disjoint. If they were disjoint, I could do them all at the same time, or several at the same time, but you see that there's 7 and 7 here, there's a 3 here and a 3 here, and then a 1 and a 3 here. So as I go down, I have to do them one by one. Okay, so 4, 7, 3, 5. 4 goes to 7, 7 goes to 3, 3 goes to 5, and then 5 goes back to 4. Everything else stays the same. Then 9, 2, 6, 3, 1. 9 goes to 2, 2 goes to 6, 6 goes to 3, 3 goes to 1, and 1 goes back to 9. Then 1, 3, 4. 1 goes to 3, 3 goes to 4, 4 goes back to 1. That's the answer. So then this really, I mean, of course, we basically forget about all our scratch work. And this symbol is, this permutation is right here. So then now I'm going to write it out. 1 goes to 9, 9 goes to 3, 3 goes to 5, 5 goes back to 1. We're done with that. Then 2, 2 goes to 6, 6 goes to 4, 4 goes to 7, 7 goes to 8, 8 goes to 2, so we're done. So that's what the answer should be when we do the all the little ones, all the 2 cycles. I'm going to do the 2 cycles lengthwise. And there's a whole bunch of them. So 1, 2, 3, 4, 5, 6, 7, 8, 9. I'm just going to write them out. So 7, 8, 7, 9, 4, 7, 4, 3, 4, 5, 9, 2, 9, 6, 9, 3, 9, 1, 1, 3, 1, 4. Okay, so that's all of them. So 8 and 7, and then 7 and 9, then 4 and 7, then 4 and 3, then 4 and 5, then 9 and 2, then 9 and 6. 6 was here, 9 goes here. Then 9 and 3. Then 9 and 1. Then 3 and 1. Then 1 and 4. Yep, I think that's what I should get. So I got so I got 96, 57, 14, 823.